Hello everyone. In this video we look at one of the other important aspects in this units and measurement topic, which is about the measurements. Now when we look at certain measurements, like say for example we talk about the Avogadro number, we always give the value of Avogadro number as 6.022 into 10 power 23. Whereas if we talk about the speed of the light, we will say speed of the light is 3 into 10 power 8 meter per second. Now, what is the reason why we are showing the Avogadro number as 6.022 into 10 power 23 and the speed of the light in most of the cases is only 3 into 10 power 8. If you look at some of the other the standard measured values that we will be using, like say for example we talk about the Planck's constant, so we always represent it as 6.626 into 10 power minus 34 joule into second, and the mass of the electron we always represent it as 9.1 into 10 power minus 31 kg. Why is it that the number of digits that we have in say for example the Avogadro number and Planck's constant are higher, whereas the number of digits that we are representing in the speed of the light as well as the mass of the electron, these two are lesser? What exactly is the reason for that is what we'll be learning in this concept of significant figures. Now, what are these significant figures actually? When we have a measured value of any physical quantity, then the number of digits which we have confidence is what we'll be calling as the significant figures. There is a procedure to find out what is the number of significant digits in any given measured value, but the idea is larger the number of significant figures, it means we have more confidence in that particular value, or we can also say there is a greater accuracy in the particular value of the measurement. So this is the broad idea of what is significant figures. Now looking at the rules that we follow to find the number of significant figures in a given measured quantity. The first is whichever measured value is there, all the non-zero digits in that measured value will be significant. Means if I have 42.3, in that all the three digits 4, 2, 3, all of them will be significant. If I have 243.4, all the 4 are non-zero, so they will be significant. If I have 24.123, all the 5 here are non-zero digits, so they will be significant. And here we can see with these three examples that the confidence level in this 24.123 will be higher, and the confidence level in this 42.3 measurement will be the least. So this is the first rule of finding the significant figures, where in any given measured value all the non-zero digits will be considered as significant. The second rule is about if you have 0 which is between two significant figures, then the particular 0 also will be significant. Means if a 0 is appearing between two non-zero digits, like in the case of 5.03, we can see 0 is appearing between 5 and 3. This 0 will be significant. Similarly in 5.604, this 0 also will be significant. In 4.004, both the zeros, because they are between two non-zero digits, both of them will be significant. Thereby the total number of significant figures in 4.004 will be 4. Already both the 4s are significant, and these two zeros are also significant because they are in between two non-zero digits. Moving on to the next rule, if we have leading zeros which are placed to the left of the number, now the zeros which are on the left of the number we call them as leading zeros, and the zeros on the right of the number we call them as tailing zeros. Leading zeros, which will be placed to the left of the number, are not considered as significant, so they will never be significant, which means in 0.543 this 0 will not be significant. In 0.045 both the zeros are not significant. In 0.006 all these three zeros are not significant. So whatever the number of zeros which are onto the left side of the number, they will not be significant. Trailing zeros or the zeros placed to the right side of the decimal number are significant. Means if I have 4.330, this 0 will be significant. 433.00, these two zeros are also significant. 343.000, all the three zeros will be significant. So here we are looking at the trailing zeros which are placed to the right side of the decimal number. Now we are focusing on the decimal number. If we go to the whole number, then the trailing zeros are not considered as significant. So if I simply give 5400 as a number, then these two zeros are not considered as significant. But here there is an exceptional consideration. If these zeros are a part of the measured value, like we express the value with unit. If we say 5400 kg, then in that particular case the two zeros will be considered as significant. So thereby in the 5400 kg, the number of significant digits will become 4. Whereas if I simply give the number 5400, then we will not be considering the two zeros as significant. So these are the rules for finding out the significant figures. And last and probably one of the other important one is generally we'll express the numbers in the scientific notation or the exponential form. So if you have a number in the exponential form, then there will be the number part and the exponent part. The significant figures of this particular number will be only given by the significant figures of the number part, and the exponent part we will not be considering for the significant figure calculation, which means in 1.32 into 10 power minus 2, the number of significant digits is 3. In 1.32 into 10 power 4 also, the number of significant digits is 3, because the number of significant digits depends only upon the number part of the exponential notation or the scientific notation. While we are doing some measurements, there will be a certain situation where we may have to round off the number. Now why exactly we need to round off the number, we will be able to understand when we go to the next stage of this discussion. But when we have any measured value, and using the measured value we are trying to derive a particular value, like say for example we measure the length and breadth of the rectangle and we are trying to find the area. Now the area is actually called as a derived value. The confidence level in area will be the least of the two confidence levels, in the sense we measure the length and we measure the breadth. The accuracy in that area measurement cannot be more than the accuracy of the least. Like say for example we are measuring length and we are measuring breadth, one of them will be having a lesser accuracy. Then definitely the area also cannot have more accuracy than this particular least accurate measured value. So with that we will be required to do some rounding off of measurement, and we'll take a look at it when we go to the next stage of the discussion. But here we'll try to understand how do we actually go about doing the rounding off. Now if we have a number, like say for example the number is 7.82 and we want to round off the last digit. If you are trying to round off the last digit, and if the last digit is less than 5, then simply we will drop that digit, and the preceding digit remains unchanged. Means if I need to round it off to one place less, then 7.82 will simply become 7.8, because the digit that I am rounding off to is less than 5. Similarly, if I am trying to round off 3.92, the digit that I am rounding off is 2, which is less than 5, so we'll just simply drop it, and no change will be done to the preceding digit. Whereas if I go to the case where the digit to be rounded off is more than 5, then as we can see in this example, if I need to round off 6.87 to one decimal place less, then when we drop the 7, we will be adding a 1 to the preceding digit. Means when we round it off, it becomes 6.9. Similarly, 12.78, the last digit to be rounded off is 8, which is more than 5. So when we round it off, we add a 1 to the preceding digit, thereby it becomes 12.8. Now if the digit to be dropped is 5, so we discussed what if the digit to be dropped is less than 5 and what if the digit to be dropped is more than 5. Now we have a case where we are dropping a digit which is 5. If it is followed by digits other than 0, then the preceding digit will be raised by 1. In the sense, if I need to drop this 5, the 5 is followed by 1, which is non-zero. So which means in that case, when I am rounding off this 5, I will be adding a 1 to the preceding digit. Means it becomes 16.4. Similarly, if I need to round off this 5, here after 5 there is an 8, which means when I round it off, it becomes 6.8. Now if the digit to be dropped is 5 or 5 followed by zeros, if it is 5 or 5 followed by zeros, then the rule is, if the preceding digit is even, then we will simply drop the 5 and no change will be done to the preceding digit. Which means if I am trying to round off 3.25 or 3.250, the preceding digit to the 5 is 2, which is even, so we will simply drop the 5 and no change will happen to the preceding digit. Similarly, if I am trying to round off 12.650, here I have 5 followed by the 0, the preceding digit is 6, which is even, so I will simply drop the 5 and no change will be done to the preceding digit, so thereby it will be 12.6. If the number to be dropped is 5 or 5 followed by zeros, then the preceding digit is raised by 1 if it is odd. Like in the case we can see 3.750, so the preceding digit to 5 is 7, which is an odd number, so we'll round it off to 3.8. Same is the case with 16.150 to the 5, we have the preceding digit which is 1, which is an odd number, so it will be rounded off to 16.2. So these are the rules that we have in terms of rounding off. Now the purpose of this rounding off is basically the reason why when we have measured values from where we will obtain the derived values. Now in most of the experiments we will be having observations of various measurements which we will combine mathematically. Like we may add, we may subtract, we may multiply, we may divide to get the final result. Like if I talk about the area will be equal to length into breadth. If I talk about the volume will be equal to length into breadth into height. Of course I am referring to the example of the cuboid. If I talk about the density, then density will be equal to mass by volume. We may have cases where I have a measured quantity A and B, and by adding both of them we may get a derived value X, or sometimes by subtracting them we may get the derived value Y. So if you look at the operations that we will be performing in terms of arriving at the derived value, we may have addition operation, we may have subtraction, we may have multiplication, or we may even have division. Now if you look at the measurements, as we probably just discussed a little while before, the measurements will not have the same precision. So if I am trying to find the mass using a particular instrument and I am trying to find the volume using another instrument, the precision value in the mass and the precision in the volume may not be same. And if these two are not same, it is natural that the final result cannot be more precise than least precise measurement. So if I am trying to operate 2 or 3 measured values to get the derived physical quantity, then the derived physical quantity cannot be more precise than the least precise of the measured values. To obtain, how do we go about finding the significant figures? in the calculation of any derived quantity, we'll follow two rules, and we'll look at the two rules with specific examples. The rules for the addition subtraction will be similar, and that of the multiplication division will be similar. If we are doing an addition or subtraction operation, then the final number which we will have after the addition or the subtraction operation will have the same number of decimal places which are present in the number which is having least number of decimal places. So if I am adding three numbers, then in the three numbers, say for example, one number is having the number of decimal places 2, another number is having number of decimal places 3, another number is having number of decimal places 5, then the final value must be rounded off in such a way that it will be having just 2 decimal places. So the number of decimal places in the final result will be equal to the number of decimal places of the number that is having the least number of decimals. So we'll take a look at it with this particular example. Let us say we are adding 33.3 with 3.11 and 0.313. So here this has got 1 decimal place, this has got 2 decimal places, and this has actually got 3 decimal places. But as we just saw, the result must have the number of decimal places which is equal to the decimal places of the number with the least decimals, and it happens to be the 33.3, which has got only 1 decimal place. Now when we are adding these numbers, we'll simply add them. So the rounding off will not happen before the addition. So first we'll simply add them, and when we add them, the result is 36.723. Now this will be rounded off in such a way that we will just have 1 decimal place. Starting from 3 is a number less than 5, so we'll drop it. Then 2 is also a less than 5 number, so we'll drop it. Thereby the final answer will be 36.7. We can look at another example in case of subtraction. Let us say for example we are subtracting the 24.5492 from 62.831. Now in these two, 62.831 has the least number of decimal places, which is 3 decimal places. 24.5492 has 4 decimal places. The subtraction result will be 38.2818. Now this has to be rounded off in such a way that we'll have 3 decimals. So when we are trying to round off 8, which is a number more than 5, when we drop it, we have to add a 1 to the preceding digit. So thereby the rounded off value becomes 38.282. So this is what will be the case in case of addition subtraction. Now moving on to the rule for the multiplication and division. When we round off the final number, the rounding off is done in such a way that the final result will have the same number of significant figures which is possessed by the least precise term used in the calculation, which means in the case of addition subtraction we talked about the rounding off to be done by using the decimal places, but here in case of multiplication division the rounding off will be done by using the significant figures concept. So when we are doing a calculation with say for example 3 numbers, one number has got 2 significant figures, another number has got 4 significant figures, another number has got 6 significant figures. When we round it off, we should round off in such a way that the final calculation will be just having 2 significant figures. So here the rule is about the significant figures. Let us look at it with an example. If I have 142.06 to be multiplied with 0.23. Now in this case also there is not going to be any rounding off before we do the calculation. So when we simply multiply the given numbers, we get the result 32.6738. Now in the two measured values or the values used, 142.06 has actually got 5 significant figures because there are 4 non-zero digits and the 0 is between 2 non-zero digits, so that also becomes significant. Total number of significant digits is 5. Whereas in 0.23 the 2 and 3 are significant, 0 is not significant because it is the leading 0. The 0 is on the left side of the number. So between the two values that we are using for calculation, 0.23 has the least number of significant figures, which is 2. So the answer also must be rounded off to 2 significant figures. So if you look at this 32.6738, we'll start rounding it off so that we'll get just 2 significant figures starting from 8. When we round off 8, we have to add a number 1 to the preceding digit. That becomes 4. 4, when we are rounding it off, it is less than 5, so we'll drop it. 6, 7. 7 is a number more than 5, so we'll add a 1 to the preceding digit. So it becomes 32.7. 32.7, when we are rounding it off, it is more than 5, so we'll add a 1 to the preceding digit, thereby it becomes 33. So this is the rule that we follow in case of the significant figures calculation using multiplication. Let us look at another example for the division. Here we have 0.90 divided by 4.26. The result is 0.2112676. If you look at the significant figures in 0.90, this 0 is not significant, 9 is significant, this 0 also will be significant. So totally 2 significant figures. The denominator has 3 significant figures. The final value will be rounded off to just 2 significant figures, which means it will be rounded off as 0.21. Now for the rounding off, we will be exactly following the rules that we discussed previously. So this is about the method that we follow to find the significant figures in a calculation. Now when we talk about generally a representation of numbers, commonly we will be referring to the scientific notation. So scientific notation is basically if we have a number expressed as m into 10 power x, where m is a number between 1 to 10, should not be 10, and x is an integer. It may be a positive integer, it may be a negative integer. So this is what we'll be calling as the scientific notation. Generally, when we talk about numbers, or when we talk about even expressing the final value of the calculations, we'll try to represent this in the scientific notation. Now when we try to represent a number in the scientific notation, we talk about something called as the order of magnitude. So we'll say these two quantities are in the same order, these two quantities are not in the same order. So let us look at what is this order of magnitude. Now order of magnitude of any quantity, right, is the power of 10 which is required to represent the particular quantity. It's a very basic understanding of what is an order of magnitude. Now for finding out the value, we need to do little bit of rounding off. So what is this rounding off approach? Now the rounding off approach is, if we have, say for example, the representation of number like speed of light in vacuum, which is 3 into 10 power 8 meter per second. Here we see that this number 3 is less than 5. When it is less than 5, then we'll simply drop this number, where we'll ignore the number. So the order of magnitude is simply 10 power 8. Whereas if you talk about the mass of the electron, which is 9.1 into 10 power minus 31 kg, the number part here is more than 5. So which means we cannot drop off this number. If it is more than 5, then we will have to add a 1 to the power of 10, which means already the power of 10 is minus 31. We have to add a 1, means it will become minus 30. So that will be the order of magnitude for the mass of the electron. So this is the simple rule that we have to find, that we have to follow to find the order of the magnitude. Now, order of magnitude is a very important aspect while we are talking about comparing different quantities in science or in general in calculations.